Hello, in this class we will discuss with respect to staircase. So this is the design problem you can expect for full 20 marks, one question in your final examination. So generally we are having for your syllabus two types of staircase. One is dog-leg staircase and open well staircase. So here we will go for dog-leg staircase problem. So dog-leg staircase problem is very important. So here you see the question. Generally, if you have design problem or analysis problem, first you have to read the question carefully, then analyze the question and proceed with step by step. So in this problem, design a dog-leg staircase for a public building. Given the following data, so we are going to design a dog-leg staircase for a public building. And for the given data, the first data given is clear dimension of stair hall. It's a clear dimension, not wall to wall. So inside dimension, clearly what appears inside the room, that is 3 by 5 meters. And height between the floors, so we are going to design a dog-leg staircase when the height of floor is 3.5 meters and rise and tread is given as 150 mm rise, 280 mm tread. Generally in design problem, if any data are missing, then you have to assume the appropriate data. In some question, they will not give rise and tread values. If they will not give rise and tread values, then you generally assume rise in between 100 to 160 mm. So here they are given 150 mm tread in between 250 to 300 mm. So generally you can assume the value. So here, but in this case of problem, they have clearly given that rise is 150 mm, tread is 280 mm. So width of flight, so the landing width, which both are equal to 1.45 meters. And assume the stairs to be supported on 230 mm thick masonry wall at the outer edge of the landing. This is also sometimes they won't give. They will simply mention the stairs rest on a wall. So in that case, you have to assume the proper thickness of the wall, 230 mm, 250 mm, 200 mm as you wish, but you have to assume appropriate, adequate in between values. So and also the landing is packed to rise, use M20 grade concrete, Fe415 steel. This is very important. The grade of concrete and grade of steel. And also sketch the details of reinforcement. So these are all the given data for the design of dog-leg staircase as per limit state design, that is IS 456-2000. We have to accommodate for this design. So we will proceed with step by step. The very first step in the case of design of dog-leg staircase is arrangement of stairs. So we know the rise value, we know the tread value, but we don't know how many rise is required and how many treads are required in each flight. So we know that in dog-leg staircase, we are having two flights, one flight in this direction and then in opposite direction. So for that we have to be calculate what is the number of threads required and what is the number of rise required. So now we proceed with, in very first step we are going to deal with the arrangement of stairs. Arrangement of stairs. Step 1. Arrangement of stairs. So here you have to see that number of rise. How to compute number of rise? Number of rise. For the calculation of number of rise, first we know the floor height. So floor height divided by what is the value of rise. So the floor height divided by rise. Floor height by rise. What is the floor height? The floor height is given as somewhere landing width of flight. Floor height between the floors is 3.5 meters. So 3.5 meters, you can say 3500 mm. What is the rise value? Rise value is given as 150 150. So please compute what is the number of rise. Number of rise is coming around 23.3, which means you have to round it to 24. So we cannot provide 23.33. So we are round it off to 24. This is the number of rise. Similarly, number of what is the actual rise now? Actual rise. See, we are having 24 numbers. So what is the actual? So now 3,500 divided by 24. What is the actual number of rise?
145.8.
145.8. 145.8. But we have provided 150 mm. Clear? Actual rise is what we are going to provide, that is 145.8 mm, but they have given us 150 mm. No worries. Okay, clear? Next, number of rise from the flight. So there are two flights. This is the total number of rise, but in Doglegged we are having two flights, right? One flight in this direction, then we are having landing in opposite direction. So we are having two flights. So we are getting what is how many number of rise in each flight? 24 by 2. Number of rise in each flight. How much? In each flight is 24 by 2 is 12. So we are getting 12 flights in each. Clear? So number of threads generally what happens? So one rise flight, right? So we are getting. So this is rise, this is thread. This is rise, this is thread. So generally what happens? So number of rise. You see, we are having now 2 steps. In 2 steps, how many rises are there? 1, 2, 3. How many threads are there? 1, 2. So number of threads is less than 1. Right? So now number of threads in each flight is 12 minus 1. How much? 11. So number of threads in each flight which is equal to 12 minus 1, this is 11. So this is very simple. You just observe there are 2 steps. So we are having 1, 2, 3 rise, 2 threads. So in each flight we are having 12 rise. So in each flight we are getting 1 number less threads. So 12 minus 1 is 11. So this is the very first step. Now we just decided what is the number of rise and what is the number of threads in each flight. Now I am going to sketch the details. It's very simple one. First you observe what is the room dimension. 3 meters by 5 meters. The room dimension is 3 by 5. The room dimension is 3 by 5. So this is 3 meters and this is 5 meters. 3 by 5. Now I want to divide how many threads, how many rise. I'll write a simple plan. And also you know that what is the thickness of wall? The thickness of wall is 230 mm. The thickness of wall is 230 mm. So first I'll write a room like this. Now, so in each flight, how many threads in each flight we are getting? The first thing is in ground floor. This is ground floor. We'll remove this. Just please. Say this is opening wall. Say this is ground floor. Now, so what is the landing width? landing width is 1.45 meters. Landing. So here you just provide landing width of 1.45 meters. So total 5 meters. So number of threads are 11, right? Number of threads are 11. You have to sketch in such a way that this is the direction from ground floor. So up to say this 3, 4, 5, 6, 7, 8, 9, 10. How many numbers? 11. Next. So calculation is very simple. You know this. 11 into what is the thread width? 11 into 280, which means meters. 0.28. 0.28. How much? 280 mm. I am written into meters. 0.28. 11 into 0.28? 3.08. 3.08 meters. 3.08 meters. Next, I know the landing. Landing is given. How much? Landing. How much landing? What is the landing width? 1.45 meters. Then the remaining distance is very simple to compute. 5 meters. 5 minus 1.45 minus 3.08. How much?
0.47.
Yes, 0.47 meters. So any doubts to compute this? Number of threads we know that 11 threads, 11 into 280 mm, 0.28 meters, we are getting 3.08 meters. And this 1.45 meters is given in the problem. So I have just drawn this 1.45 inner. Next, the remaining thing, 5 minus 0.45. So this is the room you are entering. So when you are getting the staircase, so up to you are having 12 rides, 11 threads. So I have given a number. Then you are getting landing like this, right? So here also in the you know the landing. What is the landing width? 1.45 meter. Here also you know the landing width. How much? 1.45 meter. What is the remaining thing? So the total 3 meters. 3 meter minus 1.45 minus 1.45. So
0.1.
How much?
0.1.
Yes, the gap between this is 0.1 meters. Then you are getting the total of 3 meters. So this is 3 meter, this is 5 meter. See here also the same thing. Next slide. One, two, three, up to 11. So any doubts? So when from ground floor to you will reach here first floor. This is the plan. This is the very first step. Any doubts? This is very important and simple step in case of dog-leg staircase. Design of dog-leg staircase. That is arrangement of stairs. We have to arrange a stair in such a way that you have to design it 2 flights. So we know the thing, the floor height. In floor height, we will compute number of rise. So this, you don't think like actual rise and all things. You just remember this one. Then you go to calculate what is the number of rise in each flight. So we are having 2 flights. So 12 number of threads. 12 minus 1, 11. Next, using number of threads, write a schematic plan of staircase. Clear? Next, second step, load calculations. This is also very important step. Load calculations. This is very important. What are the different types of loads are acting on the stairs for the design purpose? Okay. So the very first thing is first. You know that staircase is like this. We are having weight slab also, right? This is slab. We call it as weight slab. So first we have to assume the slab thickness. Generally we will assume like 100 to 150 mm. In this case I will going to, they are not given the waist slab thickness in the problem. So generally in design or analysis problem, if they are not given, we have to assume properly suitable data. In this case I am going to assume waist slab thickness which is 150 mm. Slab thickness 150 mm. So if you are assuming 150 mm overall thickness, then what is the effective depth of the waist slab? The effective depth of the waist slab is computed by overall depth minus, we have to remove a cover. Generally we will assume a cover of 20 mm, and I am assuming the reinforcement of main bar, okay, as 10 mm, say 10 mm I am assuming, then half of the bar thickness, so 10 by 2, then what is the effective thickness of this waist slab? So this is total depth minus cover minus half of the reinforcement thickness, 10 mm generally we will assume 125 mm. This is the effective depth of the waist slab. So general design, when we go to beams or slabs, these are the things we are going to assume, covers and thickness of the bar. Clear? So next, first we know in this the very first thing is dead load of the waist slab. How to compute dead load? Thickness multiplied by density of the concrete. 0.125. What is the density of the concrete? In RCC we will assume 25. Right? How much? 3.125. What is the unit? Kilonewton per meter square. This is the first thing, dead load. First we computed the waist slab thickness. Using the density of concrete we multiplied it. Then we are getting the dead load of waist slab. The load alone in this direction is 3.25 kilonewton per meter square. Next, second one. Load, see here once again we are having two cases. One we are getting like the waist slab slope. This is slope, right? Waist slab generally is slope. In slope we are having both horizontal direction as well as the steps, like one vertical, horizontal, right? So this is dead load of slab on slope, but landing horizontal is there, another one. We have to compute both the things and we have to add, then we are getting total weight of the waist slab. Clear? Total dead load. So load on horizontal, so this is slab on slope. So next here we are having another thing is horizontal. How to compute horizontal weight? For this you have to remember one equation. The equation is 3.75 square root of rise square plus thread square divided by thread. So what is the value? 3.75. So square root of rise. What is the value of rise? The value of rise is 150, right? 150. The value of thread is 280 square divided by 280. So how much? See, this is here. Please note that here you can use whatever the calculated value 145.8. 145.8 means 146 you may use, or you use 150. No problem. It's also right. How much? Weight. What is the weight? So you are getting around 4.23. Value 4.23. Please check. 4.23 kilonewton per meter square. Okay, right. Next, dead load of each step. We are having each steps. Dead load of each steps. How to compute dead load of each steps? That is, you have to remember one equation: rise by 2 multiplied by density of the concrete. What is the rise value? 146 by 2 into 25. See, why we are using 146 actual? To reduce the design, to design a safest economical section. If you use 150, your weight is high, right? So that's the thing, we are adopting actual rise. Yes, how much? 1.82, right. 1.82 kilonewton per meter square. 1.82. Next. So next we are using floor finish. We will assume 0.5 kilonewton per meter square. For stairs, floor finish we will assume 0.5 kilonewton per meter square. And live load for public building, because the problem is clearly mentioned that it is a public building, right? So this is one more code available on loads. Okay, so as per the code, live load, you remember this, live load for public building is 4 kilonewton per meter square. 4 kilonewton per meter square. Then you compute the total load. What is the total load? Add all 4. Then you are getting total load. How much? What is the total load? Add all 4. You are getting total load. What is the total load? 9.445. So approximately 10. We'll take as 10. Right? 9.445. And also this 0.5. Each and everything you add. This one 3.125 plus 4.23 plus 1.82 plus 0.5 plus 4. So 10.55 kilonewton per meter square. Please check. 10.55 kilonewton per meter square. 10.55 kilonewton per meter square or 10. No issues. You can take 10 or 10.55. Okay. So higher than, please check twice. Okay. If it is 10, you take 10. Okay, no problem. So this is the total. This is the total. This is very important step. Very important step. Step number 2, load calculation. Okay, ultimate load. This is the working load. How to compute ultimate load? Factor of safety. Ultimate load is computed using this working load multiplied by factor of safety. So ultimate load is given by 1.5 times of 10.55. How much? 15.825. 15.83 kilonewton per meter square. This is the ultimate load. This is step number 2. In first step, we have just planned the stair. In second step, we calculate the load on stairs. Next, in third step, we are going to analyze. In last step, we are going to decide. That is the thing. And finally, we have to sketch the details. Any doubts? Next, the third step is analysis. So for analysis, load on landing. Once again, see, these are loads on weight slab. Landing is also there, right? So generally, where stair looks like this, right? We have computed this one now, and also we left with landing. Okay, loads on landing. Now I just erase this one. Load on landing. Load on landing. How to compute load on landing? How to compute load on landing? So we are going to compute load on landing. First, you provide the thickness of landing, which is equivalent to thickness of base slab, right? So when you are providing a base slab thickness is 150, the landing also will provide 150. If you 120, then you provide 120. In this case, we have provided a thickness of base slab as 150. So here also assume the thickness of landing slab is also 150. So 150 mm. So dead load. So assume slab thickness 150 mm. 150 mm. So dead load on landing is 150 dead load. So now dead load on landing is 0.15 multiplied by density. How much? 0.15 into 25? 3.75 kilonewton per meter square. And similarly, you take floor finish and live load. Similar values. What is the floor finish? 0.5 kilonewton per meter square. What is the live load? 4 kilonewton per meter square. What is the total? What is the total? 8.25. What is the ultimate? 8.25 kilonewton per meter square. So ultimate landing load. What is the ultimate load? 1.5 multiplied by working load is 8.25. How much? 12.375. So which means 12.38. Right? 12.38 kilonewton per meter square. This is another ultimate load. So this ultimate load is for here. This ultimate load is for landing. So we got two ultimate loads. Any doubts? One ultimate load is 15.83. Another ultimate load is 12.38. Now it is very simple. You just observe here. See, I will take like ABCD. Four corners are there, right? So I will name as ABCD. I will name as ABCD. Consider the flight CD. See, if you consider the flight CD, so this distances, same distances you should carry, but including wall thickness, half of the wall thickness you are consider simply supported like this. So here you are having landing, right? Here you are having landing up to here, landing load. Then your weight slab load, that is stage load. Next once again landing load. So this is half of the wall. So the distance is just revised distance is 1.45 plus 0.23 by 2. 1.45 plus 0.23 by 2. How much? This is 3.08 meter only. This is how much? This one? 1.565 meters, and this one 0.47 plus 0.23 by 2. 0.585 meter. So this load is how much? 12.38 kilonewton per meter. Then this one 15.83 kilonewton per meter. This one is once again 12.38 kilonewton per meter. These are the values we calculated in previous steps. Now you say this is C and this is D. We have to compute VC and VD values. How to compute VC and VD values? This very simple thing. Apply equations of equilibrium. Sigma V equals 0. For this, all upward force are are positive and all downward force are negative. So this load you convert into point load. How to convert UDL into point load? The conversion of UDL into point load is load into distance. Load into distance. So 12.38 multiplied by 1.56. How much? So 12.38. So plus BC minus 12.38 multiplied by 1.565 minus 15.83 multiplied by 3.08 minus 12.38 multiplied by 0.585 plus VD, which is equal to 0. So VC plus VD, which is equal how much? 75.373. So say equation number 1. This step have you got? Load into distance, load into distance, load into distance. Convert UDL into point load. All acting downward, that's why negative. Next you take sigma moment at C equals 0. For sigma moment at C equals 0, 12.38 into 1.565. You converted it into point load. That multiplied by distance. What is the distance? 1.565 by 2. So this is first acting clockwise. Plus. The next load is 15.83. The distance is 3.08. That multiplied by 3.08 by 2 plus the distance is 1.565. 1.565. Have you got this one? 15.83 multiplied by 3.08. That multiplied by this distance. What is this distance? 1.565 plus 3.08 by 2. Clear? Next plus 12.38 that multiplied by distance is 0.585. Point load I converted. That multiplied by the distance is 1.565 plus 3.08 plus 0.585 by 2. So this full distance here to here 1.565 plus 3.08 plus 0.585 by 2, and finally anti-clockwise minus VD that multiplied by 5.23 total distance. This total distance is 5.23, which is equal to 0. Now we are getting VD value. How much VD? We solve this. We are getting VD value. What is the VD value? 38.68 kilonewton. Now you substitute this value to equation number 1. You are getting VC value 75.373 minus 38.68. How much? 36.69 or 7 kilonewton. Any doubts? So these are reaction. Now once you compute reaction, what is the next step? Next step, I want to compute where the bending moment is maximum. Where you are getting a minimal shear force or 0, at that point we are getting maximum bending moment in case of simply supported beam. Generally, you know that if it is symmetric load, then you may expect a mid-span maximum bending moment, but it is not symmetrical load. Here we are having one weight of UDL, but here it is maximum. So it is uneven. It is uneven. Therefore, when it is uneven, at that time you have to compute a point where the value will become 0 to get maximum bending moment. For this purpose, I am considering a section. So this is C, D. If you consider a section XX, say somewhere here at this point, say XX, consider distance EX. I want to compute the distance X. How to compute the distance X? That is very, very important. If I consider shear force at X, I know this reaction value, VC value, how much? 36.7 and this value, how much? 12.38, 12.38, and this is 15.83, and this is 12.38. Now, if you take Vxx, shear force at xx, Vxx, shear force at xx, how many loads are there here? 136.7 upward. Next 12.38 multiplied by distance. This distance how much? This distance is 1.565, and this distance 1.565. This is the distance. So x minus 1.565. This distance is x minus 1.565. This is very, very important. So now only shear force, load. For UDL, load into distance. So here Vxx, which is equal to only load 36.7 minus 12.38 multiplied by 1.565 minus 15.83 multiplied by x minus 1.565, which is equal to 0. Which is equal to 0. So this is 12.38 you take here. Now 0, which is 36.7. How much? 12.38 into 1.565. Value 12.38 multiplied by 1.565. 19.374, and multiply this one, it will become minus 15.83x, minus into minus plus. What is the value? 15.83 multiplied by 1.565? 24.77. Now you solve this, you are getting x value. You solve this, you are getting x value. Please check, x is 2.66 meter. 2.66 meter from C. From point C. From C. Yes, right? Clear. So this value is 2.66 meter. Now for this point you have to compute the moment. So that is the maximum bending moment we are considering for design purpose. Clear? How to compute the x value where the shear force is 0? At that point we are getting maximum bending moment. It's the concept behind this. So next compute mu. How to compute mu? How to compute mu? It's very simple, direct moment. Mu is very simple. So now 36.7 into x. 36.7 multiplied by x minus 12.38 multiplied by, so what is the distance? 12.38 into 1.565 point load. Then the distance is how much? So load into load you convert into point load. First you convert into point load. So 12.38 multiplied by 1.565. 12.38 multiplied by 1.565. Then the distance. Then the distance is multiplied by, what is the distance here? 1.565 by 2. So which means what is this distance? 2.66 minus 1.565 by 2. 2.66 minus 1.565 by 2, or 1.565 by 2 plus this value. So for easy sake I will take as, I will compute the distance here. I will compute the distance. This distance is 2.66 minus 1.565 by 2. How much? 2.66 multiplied by 2.66 minus 1.565 by 2. 1.877. Right. So this is negative, and one more value you are having, this one minus. The load is 15.83. 15.83. What is the distance? H2 x minus under 2.66 minus 1.565 H2. 1.09. This distance is 1.09, right? So 1.09 that multiplied by 1.09 by 2. that multiplied by 1.09 by 2. First load into distance, the distance by 2. Clear? So how much have you got? 51.81. Please check 51.81. 81. Please check the answer. 51.81 kilonewton meter. Right? Once we got maximum moment using the concept, right? Okay. Next, check for depth. So we are having all values. We are having depth, waist slab thickness, thread, rise. Now our duty is to check whether the given details or assumed details for this moment is right or wrong. That is the next step. Clear? Check for depth. Next, third step. See, third step. Check for depth. Check for depth. Step 3. These are the things very simple. For this we use IS codal provision. We are having IS 45696 with us. So please follow this code book IS 456 2000. For check for depth and all, you go to page number 96 of class G 1.1 of class G 1.1, where you are getting an equation, mu limit 0.36 xu max by d. For this you have to use the equation mu limit 0.36 xu max by d 1 minus 0.42 xu max by d b d square fck. This is available in IS 456 page number 96 of class G 1.1. You have to write all these things in your final examination. Clear? So go to page number 96, write the equation. Now what is your limitation of moment? That is very, very important. You have limited your moment to one value, right? So using that value you have to check whether it is okay or not. This is check for depth. So what is mu value? 51.81, right? You are limited to 51.81. So we have to check whether it is okay or not. For the depth, what is the depth? We have adopted the waist slab and all the things. We know that. So now you just compute the value 51. See, this is kilonewton meter. So you have to substitute Newton in millimeters. So 51.81 Newton millimeters 10 power 6 ಆಗ್ತದೆ. kilonewton to 10 power 3, meter to 10 power 3, millimeter 10 power 6 ಆಗುತ್ತೆ. Clear? 51.81 into 10 power 6, 0.36 xu max by d. That is also one of the parameter. Xu max by d that is available in page number 70. You go to page number 70. Here in page number 70, it is clearly given the values for grade of steel. What is the xu max by d value? So page number 70, you go and read the given grade of steel is Fe415. From page number 70, for xu max by d for the grade of steel Fe415, the value is given as 0.48. So how we got this? xu max by d, we got it from code book of page number 70. For grade of steel Fe415, the value is 0.48. So 1 minus 0.42 multiplied by 0.48. B, breadth 1 meter. Depth always we will do for meter. 1 meter, which means 1000. into d square, grade of concrete is 20, given as M20. So D, we have to compute D. Now solve all this, check what is the D value. How much you are getting D value? Please check. 137.0. Okay, 137 meter, which is less than what we have assumed. 125, right? Greater than, right? Which is greater than 125 mm. So okay. See, we have whatever the thing. This is whatever we are getting. That is higher assumed. So it is not okay. It's not okay. Why? If it is, we have assumed it is 150, then it is okay. But we assumed 150, then effective depth will become 125. So this is not okay. Right? Because okay la? Because now namuk bandira actual moment ge you must give the thickness. Effective depth is 137. So now we have to revise. How we have to revise? On what criteria? Now your effective depth revised to 137. Clear? Now say revise. Now assume D equal 140 mm. 140 mm. Then what is D? 140 plus cover plus dia of bar by 2. Clear? Dia of bar by 2. Now your revised effective depth is, revised overall depth is 165 mm. 165 mm. Earlier you assumed as 150. So now you have revised based on actual calculated. Now I am providing 140. I am revising my design. Clear? Now D equal 140 and what is the total depth? 165. So this is the thing you have to do. Earlier we have assumed weight slab thickness and calculate the effective depth. Later in check depth criteria as per limit state of design, we are having one equation. Based on equation we computed the depth, but it is a little bit more, 12 mm. So we revised the section. We assumed the new one 140, then the thickness will become 165. Landing thickness is also 165. Weight slab thickness is also 165. This is for depth. Once you revise the section, see, majorly the important thing is slab thickness in staircase. Clear? Next, area of steel. Area of steel. Any doubts? Any doubts here? Okay. Then area of steel. Fourth step is area of steel. For this also you are having code IS 456. You are having equation. The same equation you have to do. You have to use for this. Mu equal 0.87 FYASV. See, this is the equation B. Previously we used equation C. So once again for this also use from IS 456 2000 page number 96 class G.11B. Here we used C. This is we used C. Now we are using B. So what is the equation? Mu equals 0.87 Fy AST is D 1 minus AST Fy divided by BDFCK. So this is the given equation BDFCK. Now you substitute all, compute AST. Mu we know that how much? 51.81 into 10 power 6 0.87. What is the Fy value? 415. AST we have to compute. D revised depth you use 140 into 1 minus into AST into D140 multiplied by 1 minus AST FY415 BD 1000 into D. D you know that 140, FCK is 20. You compute AST. Compute AST. What is the AST? Compute AST 1260. Please check. 0.4 mm square. Clear? AST FY is 415. FY is 415. This B always we take as 1001 meter width. Clear? BD, D is 140, FCK is 20 grade. Clear? AST 1260.4 mm square. Once you compute AST, so generally what is the minimum steel we are using? 0.12% of B, 0.12% of BD, total depth, 0.12% of, but minimum steel required as per code is 0.12% of B into overall depth, not effective depth. So 0.12% by 100 into 1000, depth is 165. How much? 198 millimeter squares. This is AST minimum required 198. Here we provided 1260. It's okay. If in some cases, if it is less, it is more, then you go for minimum steel. Clear? Now, spacing. See, initially we assumed what is the diameter of the bar? 10 mm. Right? Now we compute the spacing of 10 mm bar. How to compute spacing of 10 mm bar? Area of 1 bar divided by total area multiplied by 1000. Area of 1 bar, y into 10 square by 4. What is the total area of steel required? 1260.4 multiplied by 1000. So what is the spacing now? Compute 62.31 millimeter, 31 millimeters, or here you are having 3 criteria, or 3 times the effective depth. How much? 3 into 140. 3 into 140. How much? 420 millimeters, or 300 mm, or whichever is less. Amongst 3, whichever is less. Which is less? 62.31. We have to provide 60 mm. It's not possible to provide 62, right? So we can, in spacing you reduce, don't increase. There. So provide 10 mm dia. Provide 10 mm dia bars at 60 mm center to center. Clear? Next, distribution. See, I got the dia and spacing. Now I want to distribute, right? So distribution. Next step, distribution. How to distribute? For this, once again, what is the minimum steel reinforcement? 0.12% of gross area. Gross area, right? How much we got? 0.12% of gross area? 198, right? how much? Which is 198 mm square. You know that previously we computed, right? Now spacing of 8 mm. Spacing of 8 mm. Compute spacing of 8 mm. 8 mm bar. So 1 bar pi into 8 square by 4 area you consider from minimum into 1000. How much value? 253.86. 253.8 millimeter, or now 5 times d. 5 into 140 how much? Or 500 mm, or 500 mm for this. How much? 700 or 250 mm or 250 mm, whichever is less. Which one is less? This is 450, not 250. 450. Whichever is less. Less is 253. Provide 8 mm distribution steel. This is distribution steel. This is main steel. This is our distribution steel. This is main steel. Main steel we provided 10 mm dia bars at 60 mm center to center. So for distribution steel provide 8 mm dia bars at how much? 250 mm center to center. This is with respect to steel. Any doubts? Any doubts? Then the last criteria is check for shear. Check for shear. Then we have to sketch this main steel as well as distribution steel. Then the last step. What is the step number? Step number 5. Check for shear. Check for shear. Now you are having as per your code page number 72, class 40, page number 72. Page number 72. See, go to direct. You are having these equations here. Limit state collapse of shear, class 40. So you are having as per IS 456, page 2000, page number 72 of class 40.1. Class 40.1, you are having an equation tau v equals vu by bd. See, in code this is b suffix d. This is misprinted. Don't confuse it. You just take vu by bd. Don't take b suffix d. You take vu divided by bd. Code it is given as b suffix d. Okay, this is a one error in code. So page number 72, vu by bd. What is the vu value? We know that the vu value is given by the maximum of vc and vd, which is the higher value, 38.68 kilonewton. Right? The reaction vc vd. Right? 36.8 kilonewton reaction. The highest value. Yadappa highest value irodu 38.66 kilonewton, 10 power 3, 1000 into d, 140 we have provided, 140. So vu is greater value of reaction vc and vd. Divided reaction ನಲ್ಲಿ ಯಾವುದು highest value ಬಂದಿರ್ತದೋ the value is vu. Clear? V is 1 meter, you know that. Effective depth is 140. And what is tau v value? What is the tau v value? 0.275. 0.275 Newton per millimeter square. Newton per millimeter square. Now once again you go to code of page number 73. Page number 73, you are having table 19. Table 19, this is very, very important. Go to IS 456 code. From table 19. From table 19 IS 456 2000. Okay, 100 AST BD. Compute 100 AST by BD. See the 100 AST by BD here. So for this grade of concrete M20, M25, M30 is like this. For M20 you compute 100 AST BD, you interpolate the value. Clear? So 100 into AST 1 to, what is the value of AST? 1260.4. Main steel kottirodu. B is 1000, D is 140. How much you got? Please see, check. Have you got 0.9? So now you have to interpolate. 100 AST BD is 0.9 for M20, 0.9 and M20 grade. From table 19, what is the value you are getting? So 0.9 somewhere here. So you have to interpolate. So you are getting for M20 0.9. You are having two values. You interpolate. So interpolate. You are getting tau C. So you are getting tau C is after interpolation 0. It is in between 0.54 and 0.6. It is in between 0.54 and 0.6. So approximately 0.596 Newton per millimeter square. This is from table 19. Now you check tau V and tau C. Tau V and tau C. Tau C value is greater than tau V, hence you are safe. Tau C value is greater than tau V, hence safe, or else you have to revise the section. Clear? It's very simple thing. Shear also from code, bending, steel, and all the things are available in code. The only thing is analysis part. You have to compute the reaction bending moment. So this concludes the 20 marks problem. Then the last part is you have to sketch the reinforcement. To sketch the reinforcement, I'm going to sketch here. To sketch the reinforcement, the last part is sketch the reinforcement. And just approximation sketch I will give. Approximate sketch landing. Okay, and landing next. This one. Landing next. The waist slab. Thing. Now main reinforcement, distribution reinforcement, right? Here one. Just like this, main steel, like this. Like this. From here, it will come like this. This is not visible, like this. It is not visible actually, but here it's a reinforcement, like this. Okay. First reinforcement like this, next like this. Clear? Then like this. This is the stake. Approximation. up to like this. Complete. Next. Now the steels are placed. See distribution bars. Also it will come. Actually, this landing, what is the landing width? 1.45 meters. And here, what is this one? This landing width is 0.47 meter. And this width here, this is 3.08 meter. This each 11. Another slide like this, reverse. Clear? And this is the weight slab thickness. This is revised total depth is 165 mm. This is also the total depth is 165 mm. The effective depth is 140 mm. The main bar, this is full main bar. This main bar. What is how much main bar? Main bar dia 10 at 60 center to center. 60 center to center. And whatever the dotted line showing, this is cross like this. These are distribution bars in the horizontal direction. So these bars are how much? This is a distribution bar of dia 8 mm at 250 center to center throughout the slope in horizontal direction. Clear? Throughout the slope. This main bar is also throughout the distance in horizontal, in vertical direction of 10 mm. The center spacing is 60 mm. So these are the main thing we have to show. Landing, and this one. Slope. Clear? This is sketch. This completes your design of dog-leg staircase. One slide is enough when you ask for the sketch. Clear? So once again, I will explain in brief what are the things we discussed now. So this is very important problem. Design of dog-leg staircase. See whether it is open well. This is also similar. The steps all are similar only. Clear? So design a dog-leg staircase for a public building. Given the following data, inner dimension of room. This is very important. Based on inner dimension only, you will decide how many threads, how many rise you are giving in one flight. So the very first step we have done this exercise, how many rise, how many thread in one flight. Clear? Next we calculated in second step. What is the second step? Weight slab, right? Load calculation in different segments. Here load in weight slab as well as in landing. Then we draw this plan. After for this plan, we computed the loads. Based on these loads, we calculated the shear force. Where zero shear, maximum bending moment, we located the distance, we computed the maximum moment. For that maximum moment, we computed the steel using IS 456 page number 96, right? There are two equations in G 1.1, B and C. We computed AST. Then we checked for depth, effective depth. If it is not okay, revise the depth, whatever you are getting the actual thing. And finally, we checked for shear using page number 72 of IS 456 class 40.1. From table 19, we got shear is safe. Then we sketch the details. This is about dog-leg staircase. Very simple and important. Clear? Thank you.